Myself, I've been with Cisco for the last couple of years plus. I initially started off with working on ASA platforms, and right now I support FirePOWER as well as the FirePOWER threat defense platforms as well. So that's a brief intro about myself. So going ahead with today's agenda, we are basically looking into the introduction of the architecture of the FTD platform, as to how the traffic flow is going to be in an FTD platform. And along with that, will be looking into the flow offload functionality, which is available in the 9300 and the 4100 platforms for the FTD platforms again. So this is the basic architecture, or we can probably say how the FirePOWER threat defense actually came up with. So we have the ASA, which is performing the layer 2 to L4 functionality. And then we have the FirePOWER, which is mainly for layer 7 functionality. And these two have been integrated to form a common platform called as the FirePOWER threat defense, wherein we use the combination of both ASA and FirePOWER at the same time. And in case of FirePOWER threat defense, we have two ways of management here. One is the FirePOWER Defense Manager. This is currently available only on the normal ASA platforms, basically your 5500X platforms, as well as the 2100 series platforms. And then you have the off-box management as well. The off-box management is available for all platforms, but the on-box is not available for 4100 and 9300 platforms. So we do not have an on-box GUI for the 9100 and for the 9300 and the 4100 platforms. It is just off-box is only going to be managed by FMC and nothing, and we do not have the on-box management for that. So moving on, this is going to be the software architecture. It is more of a high-level diagram on what exactly happens with a packet flow from an FTD perspective. So as you can see, the initial traffic will be processed by the ASA engine, and then as the flow progresses through, we start sending the traffic to the SNOT engine, and based on the SNOT verdict, the traffic is going to be sent back to the ASA engine along with the verdict of what needs to be done with the packet. And depending upon the verdict, the ASA is either going to be forwarding the traffic out or it is going to be dropping the traffic. So yeah, so we are going, it's again mentioning the same thing here. So we have the ASA engine basically would be having multiple instances of data path processors running, and the ASA will be mainly looking into the layer 2 to layer 4 functionality. So all TCP checks, routing, all routing, and any layer 2 functionality, that is all going to be performed by the ASA engine. And then the SNOT, the traffic will then be sent to SNOT, and we will be basically doing. Yes.
Rahul, sorry to interrupt. We have been receiving complaints that the screen is not visible. Can you just try stop and resharing again? I
Sure.
can see it though.
Share again. Okay. Is it visible now?
Yeah. Thank you.
Okay, I'm just restarting this once again. So this is the FTD software architecture. So the FTD software architecture is mainly composing of both the ASA engines as well as the SNOT engines. So the traffic initially comes in on the ASA engine, and it is being processed initially by the ASA part, and then subsequently the traffic is then sent to the SNOT engine, and then the SNOT would basically send the traffic back to the ASA along with a specific verdict on what it needs to do with that specific packet that it has received. The verdict can be something like, whether you permit the traffic or you drop the traffic. And then there is an additional verdict called replace, wherein if in case you're doing some sort of TCP normalization, wherein you're modifying the TCP level packet information, at that stage you get a verdict called replace. and that's what we basically see in this specific flow diagram here. So starting off, the ASA would be having multiple instances of data path, and the ASA will be completely focusing on L2 to L4 functionality. So the ASA alone will not be doing any layer 7 functionality here. The Snort engine is what is mainly focused on layer 7 functionality. So yeah, as I mentioned earlier, the packet first ingresses the ASA and it is handled by the ASA part. And then if the policy dictates, the packet is then sent to the Snort engine. So we have quite a few actions that can be set on the ACP policy in FTD. So depending on the action that you are setting, the traffic will be sent to Snort engine for further processing, or it can be completely bypassed, wherein at that stage the traffic will only pass through the ASA engine alone and it never reaches the Snort. So the third section is, once the traffic is sent to Snort, the Snort engine would return a verdict for the packet and whether it has to be permitted through or if it has to be dropped. And then depending on the specific verdict that the Snort engine replies back, the ASA will be either forwarding the traffic or it is going to be dropping the traffic. Now we are moving on to the 9300 and the 4100 architecture and how the packet flow looks like in these platforms. So as you can see in this diagram, we have network interface, network Ethernet modules. So these modules that you're seeing is your external facing ports that we have on the 4100 and the 9300 platform. These network modules basically have an internal uplink or a backplane connection which connects to the MIO switch fabric. And from the MIO switch fabric, we have two uplinks to each security module. Now, for example, in the 9300 platforms, we can have up to 3 security modules, while in the 4100 series platforms, we have only 1 security module. So in 9300, you can basically make an assumption that, there is going to be the security module that you're seeing here. You would basically have up to 3 security modules here. And for each security module, you would be having 2 uplinks, 2 backplane interfaces. And each of these backplane interfaces will be a 40 gig uplink. So basically giving you a theoretical throughput of around 80 gig of throughput on these 2 backplane uplinks. Now, on these security modules, you can run any sort of an application here. So we currently are supporting the FirePOWER threat defense as well as the ASA application. Now, in this architecture, we are mainly focusing on the FirePOWER threat defense. And along with the FirePOWER threat defense, we can also install something called as a decorator application. And currently, we support what is called as a Radware VDP, which is mainly used for DDoS protection. So that is what we see over here as VDP. And now this is how the traffic flow basically looks like. Now initially the first packet comes in on the network Ethernet modules, and once the packet arrives on the network Ethernet modules, it is then sent to the MIO switch fabric. And from the switch fabric, the traffic will be hashed and it would be sent to the VDP initially. That is in case if you have installed a VDP application. But in case if there is no VDP installed, the traffic would be sent to the FTD directly or the ASA directly. So in this case, I have a VDP installed, because of which the traffic is first sent to VDP for DDoS. And once VDP is done with it, it would send the traffic back to the MIO once again. And at this stage, MIO then sends the packet to the security module, and this can be, at this stage is when the FTD would first receive the traffic. And now assuming a condition wherein if there's an already existing flow present on the chassis, and if I'm considering this to be a 9300 platform, and if I have set it up as an intra-chassis cluster, wherein all the security modules basically are running FTDs and they are running as a cluster. So if I have an already existing connection, the MIO switch fabric is the one which ensures that for a specific flow or for a specific connection, the traffic is always sent to the same security module. So that is what this statement means, that if there is a FTD clustering, the MIO will send the packet to the blade or the security module which originally handled the traffic. This is to ensure that there is symmetry and there is not too much of CCL redirection within the chassis itself. So the MIO ensures that the traffic is handled by the same blade. And once the packet is processed by the FTD, once it goes through the complete ASA and SNOT checks, the traffic is then sent back to the MIO directly, and from the MIO, then the packet is leaving the network Ethernet modules. This is the new 2100 series platforms, and the architecture is almost similar, but yeah, in this case, I have one internal uplink. So it starts off with the same thing. We have external interface ports here, and then we have an internal switch, and then the ASA engine runs in on an NPU, and then we have the SNOT engine. So it starts off with the same flow here. The packet first arrives on the internal switch, and then the switch forwards the traffic to the ASA engine. So this is basically the FTD, and then the ASA engine will then send the packet forward to the SNOT engine, and SNOT engine completes its processing and sends the traffic back to the ASA engine, and from the ASA engine back to the internal switch, and then back on to the physical network. So this is basically the complete packet processing which happens on the FTD. As we can see that the first section is the RX. This is basically what happens. This is from where the FTD starts receiving the traffic. So we first see the traffic on the RX queues, and then we see it on the ingress interface, and then we do the existing connection check. And if there is an existing connection, we fast path the traffic over to DAC. And yeah, I will be explaining these terms in a bit more detail in the later on slides. And if there is no existing connection, we perform the UNNAT check, which is the first step in ASA's traffic processing. And then after that, we check whether there is a pre-filter available. And if in case there is a pre-filter available, and if it is set to fast path, we again fast path the traffic. And this is one such condition wherein the traffic is not set to send to SNOT. So whenever you have a pre-filter policy, and if the action is set to fast path, we completely bypass the SNOT processing of the traffic, and the entire traffic is only processed by the ASA part, and no traffic gets processed by the SNOT engine. So if there is no pre-filter policy, or if the pre-filter policy has an action set to analyze, we go ahead with normal L3, L4 ACL policy check by the ASA. And once that check is completed, we move on to DAC, and from DAC we perform an L2, L4 decode, and then it goes through security intelligence at an IP level, and then SSL decryption, and then security intelligence again for DNS and URL, identity policy, then moving on to L7 ACL lookup. These are basically the same access control policy that you have that is configured on the SNOT side. And then we perform QoS classification, network discovery as well, and then there is file policy which is then performed, and then IPS. And once this is completed, we send the traffic back to DAC, and along with this we send a verdict as well. So if in case at any instance the verdict is set to drop, the packet is immediately sent back to DAC. The verdict is immediately sent back to DAC, and then we drop the traffic at that stage. If it passes through all the checks and at no instance we do not see a drop verdict, the traffic is then processed further, and then we create a flow update, and then we perform again. The ASA side starts performing its operations by doing the ALG checks, and then performing NAT, performing the source NAT translation, and then at this stage is when it performs the QoS enforcement. And if you have VPN, it encrypts the traffic, and after that it performs the layer 3 routing. If it finds a route, it will forward the traffic out, else it will drop it, and then it checks the ARP entry. If it is available, it will forward the traffic out, else it will drop the traffic. So this is a brief summary of how the traffic flow would look like. I would be going in a bit more detail on what is checked at each level. So yeah, this is again explaining the same thing. So the packet first arrives on the ingress interface. ASA engine checks for the existing connection, and if existing connection is not there, we then move on to unnat. So we can basically check this on the packet tracer as well. So if we do a capture, we can actually check the trace here, and at stage 1 it is unnat, wherein in this case this is considering a situation wherein we are performing destination NAT on the firewall, from the firewall side, wherein the traffic originally came in with the destination IP of 192.168.76.100, and then we are translating it to 192.168.75.14. So the traffic is first untranslated, and another point to remember here is in case of NAT, we already determine the egress interface. As you can see the statement here, the NAT divert is already determined which interface it needs to send the traffic out. So we can determine the egress interface or which interface we need to send the traffic out, either via NAT or via PBR or via route lookup. So if PBR and unnat are the first priority. If in case PBR and unnat is performing a route lookup, or if it is selecting a different egress interface, then route lookup does not happen for that specific traffic. So for example, if I'm considering if PBR or unnat tells that the egress interface has to be DMZ, but if the route lookup of that specific network indicates that the traffic has to be, say, sent out via inside, then PBR or unnat is going to take preference over the route lookup itself. So this is one thing that you need to make a note of. Then moving on, so we now move on to the pre-filter portion. So in advanced ACL, we create something called as, we have multiple access control policies that we configure on the FMC. So we, sorry. So this is an access, this is basic, when we configure an access control policy on the FMC, we basically create two sections of rules. One rule we push on the ASA side, and one rule we push on the SNOT engine. So that is wherein we basically see a layer 7 ACL, and one rule we see it as L3, L4 ACL, and one rule we see it as a pre-filter policy. So whenever we configure any ACP from the FMC, so we basically create three sections of rules. One is a pre-filter, L3, L4 ACL, and then one is an L7 ACL on SNOT. So this is how you can basically verify what is the ACP rule that you are verifying. You can verify it from Lena, as well as you can verify it from SNOT as well. So from Lena or from ASA side, it is basically we are running the same command, that is show an access list. This basically gives you the access list that is set to either permit the traffic or deny the traffic. Keep in mind that in FTD platforms, we only support global ACLs. We do not support interface level ACLs anymore. And the terminology, and on these platforms, we now start calling these ACLs as advanced ACLs, which are not the same as what we used to configure in ASA platforms. And the show ASP table classify domain permit is basically giving you the ASP table information of that specific access list that is configured. So as you can notice, the access list here is set to deny any host for any traffic from any source to the destination of 192.168.1.10. So if you check the ASP table classify domain permit, this is basically the programming which happens on from the ASA code perspective. You can see that the source IP address is 000, the mask is 0, and this port is showing up as 0 because we are matching it on IP level, and this is going to match any interface, and the destination IP is 192.168.1.10, and because this is a host network, the mask is all /32, and again, since this is a layer 3 ACL, there is no port. And as you can see, the action is set to deny is set to true, so that means we are denying this traffic. If this action was set to permit, we would basically see the deny equals to false here. But in this case, since we are actually denying the traffic, we would see the deny action is set to true. Now the same rule, we can verify this from the snort side. On the snort, we save these rules as NGFW rules. This is the location we basically store these rules under this specific location, that is /var/SF/detection engines, and this is basically the UUID of the detection engine. So we generally have only one UUID associated, so it is going to be only one. It can be any random value depending upon as long as the snort is not reloaded. So whenever the snort comes up, we basically associate it with one specific UUID, and within that directory we have something called as NGFW rules. So if you open up this file, you would basically see the same entry here. So the first one is the action, and then the next sections are for the interface, and then the first one is any interface, and the next any is for the source IP, and here we specify the port, and then again the next any is for the destination interface, and then the destination IP, the subnet mask, and the port again, and we are basically denying this traffic here. Now if you notice the rule ID, we basically have, this is an easier way to identify. So the show run access list that gets pushed on Lena, we associate a specific rule ID for it. So we have the same rule ID on Lena as well as on the NGFW rules, so that this is an easier way to identify it or to figure out which rule is seen from Lena and what rule do we see from NGFW. So we basically have to see the same rule ID in both these files, that is from Lena as well as from NGFW.rules. So now we are going into a bit more detail on pre-filter policy and how the packet processing happens at a pre-filter side. So pre-filter policy was initially introduced in the 6.1 version of code, and it is mainly serving two purposes. One is how to handle tunnel traffic. Something like this is basically has to do with encapsulated traffic, wherein you are doing something like GRE over non-encrypted traffic, GRE encapsulation over IP, or IP in IP, similarly IPv6 in IP, and Teredo port 3544. These are the four types of encapsulations that we currently support with tunnel traffic. And then the second one is we also provide early access control, which allows the flow to bypass the snort engine completely. So this is what I mentioned earlier. So in pre-filter, we have basically three actions which we can configure on pre-filter. One is fast path, and then the second one is analyze, and then the third one is set to block. So you can either block the traffic at pre-filter, or if you do an analyze, the traffic is then forwarded to L3, L4 ACL lookup from Lena. Or if the packet is set to block, or if the packet is set to fast path, we completely bypass the L3, L4 ACL lookup as well, and we bypass the DAC, and we directly forward the traffic to the flow update, and only the traffic is completely handled by Lena. So the traffic or ASA, the traffic is completely handled by ASA in this case, and we never send the traffic to snort whenever the action on the pre-filter policy is set to trust. Sorry, whenever the action is set to fast path. So this is how we configure a pre-filter policy. So under policies, we have access control, and then we have pre-filter under access control. And when we create a new policy, but the default action that we get for pre-filter rule is analyze all traffic. So that means basically, even if you do not have any rules configured here, we basically, because the default action is set to analyze all traffic, we basically forward all traffic to the next lookup, which is the L3, L4 ACL lookup. So traffic never gets dropped because you are not having any rules on the pre-filter. Now moving on ahead, under pre-filter we have two types of rules that you can configure. One is a general pre-filter rule, and one is which is used for by doing a fast path, and then the other one is a tunnel rule that we had discussed earlier, which is for the encapsulated traffic. So when you configure a tunnel policy, so this is basically a tunnel policy that we are creating. So if you notice this is how the packet looks like in Wireshark in case of a tunnel traffic, and this is the example that I'm using here is GRE over IP, wherein if you look into the payloads here, your external IP payload contains the source as destination, source as 192.168.75.15 and the destination as 192.168.77.1, and then we have the GRE encapsulation, and then within that we have the actual payload wherein the source is 10.0.0.2 and the destination is 10.0.0.1. Now in this case this is an ICMP traffic, so we are basically encapsulating this ICMP payload within GRE and then adding the extra header. Now what happens in tunnel policy with pre-filter is, from the ASA perspective, we basically only check the external payload, so which is the GRE IP header information that we are seeing, which is 192.168.75.15 and 192.168.77.1. And in this tunnel policy, if in case the action is set to analyze the traffic again, if the action is set to analyze, then the traffic is then forwarded to DAC, and we then FirePOWER processes the traffic. And now when FirePOWER processes, or when SNOT processes the traffic, SNOT will be looking into the internal payload here, which is wherein now the source is 10.0.0.2 and the destination is 10.0.0.1. So at this stage, SNOT should actually have an L7 rule or an ACP rule to permit this traffic through. If it doesn't, it would go ahead and drop it, even if you're permitting your external payload. But because now SNOT is investigating, looking into the inner payload, it should actually have an ACP rule permitting this traffic. If it doesn't, it goes ahead and drops it. But in case if that specific tunnel policy is also set to do a fast path, we again bypass SNOT completely and then send the traffic over to flow update, and then only the ASA part is checking the code, checking the flow, and traffic is never sent to SNOT. So again, yeah, here is where it mentions the rules in the pre-filter always acts on outer headers, and the rules in the ACP are always applicable to inside sessions or inner headers within the tunnels. That is what the statement means. So in pre-filter, if action is set to analyze, ASA only checks the external header, and when we send the traffic to SNOT, SNOT would check the inner payload, and if if SNOT doesn't have a rule permitting this traffic, we would go ahead and drop it, and if it has a rule, it would then permit it. And then we move on to the second type of the pre-filter policy. And here again, even in the second type of pre-filter policy, we have three actions. Again, it is basically the same set of actions again. That is, block is to drop all traffic, and fast path is it just completely bypasses SNOT, and the traffic is only processed by the ASA. And when we move on to analyze is when we send the traffic over to L3, L4 ASA lookup, and then DAC, and then SNOT engine, and then comes back over to the ASA engine. So this is how the ACL lookup looks like from the Lena side when you configure a pre-filter. So if you notice this, if you do a show access list, or you can do a show run access list as well. So you can first see the remark over here. It states as pre-filter policy, wherein this is a fast path rule. So here we create, based on the configuration that you have configured on the pre-filter policy from the FMC, you basically see a trust action here. So this is wherein you see the action as trust, and wherein you specify traffic from this source to any destination, we basically do a complete bypass. And moving on, and this is the next section here that you have is the default sections that we do. This is for encapsulated traffic all over again. So for encapsulated, these line number 6, 7, 8, 9, these are the default actions. So even if you do not have any ACP rules configured on the platform, we would be seeing these the advanced permit for IP and IP41, GRA and UDP. So wherein we would be these are for encapsulated traffic for which we perform analyze action, and then we send the traffic over to SNOT. So we will be permitting this traffic through via pre-filter policy and then send the traffic over to SNOT for additional processing. And once we complete this, we then we then see the section remark called access policy, and this is wherein your L3, L4 ACL or your ACP rules, that your access control policy rules that you're configuring from the FMC starts from this line onwards, wherein we can basically note this remark whenever you see access policy is when we start seeing your normal ACP rule configuration. Up till then it is pre-filter and the default tunnel rules that we have. Again, the ACL lookup is basically the same processing. So the first match is applied. So as long if you are having an ACL lookup matching, if you have a pre-filter rule matching, which is matching the traffic first, so we do we permit the traffic through a pre-filter, and the rest of the ACL lookup doesn't happen. So that behavior continues to remain the same here. Now, moving on to L3, L4 ACLs, we basically have 7 actions at this stage. One is wherein what we can do with the traffic. This is after pre-filter, when the pre-filter action is set to analyze, and then the traffic hits the L3, L4 ACL. So we have 7 sets of actions which can be done on the advanced ACL. The first action is allow. We basically will be allowing this traffic through from the L3, L4 ACL perspective, and then send the traffic over to DAC and then move on. And the next one is, and when we send the action to allow, the key point here is when we have the action set to allow, we basically perform the complete SNOT engine lookup. So it follows this complete path that we are seeing here from SNOT perspective. However, when we set the action to trust, we only take the path up to L7 ACL lookup and app URL, and after this the traffic is directly then sent to DAC, and we will not be performing the QoS, network discovery, file AMP or SNOT rules. So this check is completely bypassed when the action is set to trust. So the lookup only happens up till L7 ACL in case of the trust action by SNOT. And then we have the monitor rule. So when the action is set to monitor, what happens is, from an L3, L4 ACL perspective, we basically allow the traffic through and we then send the traffic over to SNOT. And when it reaches the L7 ACL lookup, what happens is we only log the traffic at that stage, indicating that the traffic is coming. However, after this, we then continue to evaluate the ACP rules even further down the list. And unless and until we have an action to again permit the traffic through, we will not be permitting the traffic. And then we would go ahead and we will be going ahead and dropping the traffic. So monitor rule basically indicates that, yeah, we are just logging that specific traffic as such, but we will not be actually permitting the traffic through. So in order to permit the traffic through, you need to basically configure another rule to allow the traffic to actually pass through. This is basically to create a condition wherein instead of enabling logging on all your ACP rules, you can probably have just one monitor rule at the start wherein you start logging all traffic coming in on the firewall, while your rest of your ACP rules doesn't really log any traffic. So that way you can actually figure out what traffic is hitting the firewall and what all traffic is being seen by the firewall. And the next action is set to block. Block is pretty straightforward. We just go ahead and deny the traffic in this case. Block with reset is, yeah, we deny the traffic and we send a reset back to the source as well. And an interactive block is a condition wherein we basically give a warning page to the end user stating that, yeah, you're not supposed to be accessing that specific resource. And we basically give the user an option on whether he wants to proceed with it or if he has to not go ahead with it. If he decides to not go ahead with it, we go ahead and the traffic gets denied. But then, yeah, he does get an option to go ahead and access that specific resource. And at that stage, we basically go ahead and log that connection event, and the end user will be able to access that resource. That is what happens with interactive block. And the next action, interactive block with reset, is basically we send a reset if in case the user chooses not to go ahead with accessing the resource. So we send a reset back to the source at that stage. So moving on ahead, we are just looking into the block action. As you can see, we have two accessless rules configured here. The first accessless rule is with the traffic from source 5555 to destination 6666. And in this case, if you notice that we are using the application as telnet, and we are choosing the action to block it. And then the second rule is traffic from 6666 going towards 7777. And in this case, instead of using an application telnet, I'm using the destination port of TCP for 23, which is again telnet traffic, and then we block it. The main reason that I'm highlighting this is there is a difference in the way that we block the traffic in these two conditions. So in case of the first condition, this is based on application. So because this is based on application, the traffic, even though you have set the traffic to block, you would actually notice that the initial three-way handshake would actually complete for this specific traffic. And after that, certain amount of traffic is actually allowed to pass through, at least until the time wherein SNOT identifies what the application is. Once SNOT identifies that the application is telnet, only then will it start dropping the traffic. Until then, the traffic will be permitted through. So this specific rule, that is rule number 1, when you set the application as telnet, the drop action is basically done from SNOT once it identifies the application as telnet. But in case of rule number 6, when you specify the TCP port as 23, the ASA will perform the L3, L4 ACL lookup and directly drop the traffic at that stage itself without sending the traffic to SNOT. So this is how we see a difference in how the traffic processing happens between when you choose application over destination port. So as you can see here, so these are the two rules that we push. So the first, if you can see the first block rule here, this is an advanced permit. We basically do an advanced permit instead of a deny. If you notice it, because from Lena side or from ASA side, we are sending the traffic through. And because the decision has to be made by SNOT depending on which it has to drop the traffic. And then if you check the rule number 6, which is deny TCP 23, yeah, we go ahead and straight away create an L4 ACL to deny telnet traffic. And if you check the NGFW rules at the same time from SNOT, we basically see it is for the same rule ID. You can notice this 35460, 35460, wherein the action is set to deny if in case the application is telnet. Yeah, this is the corresponding app ID for telnet. And then the next one is denied any 66632 host. It's a host entry for 32. And then here we are specifying the port. And yeah, this stands for protocol. Protocol is TCP, so it is 6. So this is how the NGFW rules look like for these two rules at the same time. So this is the difference that you would actually notice in the condition wherein the traffic is getting SNOT based on the SNOT engine verdict. So as you can see, this is not a SYN packet at this stage. You can see that this is a push bit flag, this is a push bit set. So we haven't dropped the traffic on the initial SYN packet itself. So we then see the action, we then see the verdict coming back from SNOT indicating that the result has to be a drop. And then we get to see the block rule ID and then the action as well. And we get to see that this is how SNOT drops the traffic. And if you check the system support firewall engine debug, this is the debug that we run from Snot at that stage, wherein you can see that it is determining that the application role is set to, application is identified as 861, which is for telnet, and then we go ahead and action is set to block, hence we go ahead and deny the traffic from Snot. And now this is how your packet tracer will look like, or your capture trace would look like when your traffic is being blocked by an L4 ACL. So you can straight away see that this is a SYN packet, and the SYN packet itself directly gets blocked, dropped, indicating an accessless drop at L4 ACL level, and we do not send the packet forward for further processing. So these are the under L4 ACL, these are the actions that we discussed. If the ACE engine is set to permit, then we allow the traffic through, and then ACE engine is set, and then if it is action is set to trust, the Snot will do a fast path, and again the fast path is basically from post L7 check. At least L7 check does happen. And then monitor rule, as I mentioned earlier, yeah, from AS's side we permit the traffic through, and then we only make a log of the traffic, but then whether the traffic has to be permitted or not, it will be decided based on the lower order rules that it has in the NGFW rules. And in case of allow, all packets will go through the Snot engine. And in case of trust, depending on the policy conditions, yeah, basically we would be inspecting at least up to L7. So that is the reason why we mentioned that few packets will go through the Snot engine, but then it doesn't go through the complete processing of the Snot engine. And in case of monitor, yeah, we go through the complete process of Snot engine as well. And again, that is considering a case wherein your NGFW rule doesn't have, say you have a monitor rule initially and then you have a deny rule for that same specific traffic, then you would probably go ahead and drop the traffic immediately and not go through the rest of the processing. But then if you have the rule to permit the traffic through, then we go ahead with the rest of the processing as well. And in case of, yeah, in case of trusted traffic, yeah, especially in case of inspected traffic, there is always, if in case you are having inspected traffic here wherein dynamic pinholes needs to be opened up, then keep in mind that that traffic has to be set, the action has to be allowed over trusted, because if there is a requirement wherein a dynamic pinhole has to be opened up, especially in case of something like an FTP traffic wherein the initial control connection happens on port 21 while the data traffic connection can happen on any random port, at that stage we need to open up a dynamic pinhole, and in order to open that pinhole up, the action has to be set to allow, else Snot can go ahead and drop it, because it will not be opening up the pinholes unless unless and until the action is set to allow. So this is something that we need to keep in mind while configuring rules, and especially in case it is something like an inspected traffic wherein you need the traffic to be inspected and pinholes needs to be opened up. And yeah, as I mentioned earlier, when the action is set to allow, we never trigger a flow offload. Flow offload basically indicating, yeah, from L7 directly to DAC, we do not do a flow offload. But in case of trust, yeah, we definitely go ahead and do a flow offload as such, wherein from L7, after L7 lookup, we directly send the traffic over to DAC without performing the rest of the checks. And in case of monitor also, we do not perform a flow offload. So there are a couple of conditions that we see. We have two separate conditions of Snot rebooting or a Snot restart. There is a slight difference between what happens between a Snot restart over a Snot reload. And we generally see this happen during policy deployment, wherein Snot can decide whether it will either reload or it can restart. So what we need to keep in mind here is during Snot reload, there is not going to be any traffic outage during the deployment. So we continue to maintain the same process ID for the Snot process, Snot detection engine, because of which there is not going to be any outage as such. But then in case the Snot restarts, there is going to be a slight outage in the traffic because your Snot goes down and then it spawns back up with a new process ID. So as you can notice here, so PID of snot is basically the command that we run from export to identify what is the process ID associated with snot. Notice that there are around 1, 2, 3, 4, 5, 6, 7 different 7 process IDs. So basically we have 7 instances of snot running here. And if you check the var log messages is wherein we see the snot restart or reload happening. And in case of FTD, we always need to ensure that you are including /ngfw. And in case of normal FirePOWER appliances which are non-FTD, the path is going to be var log messages. But in case of FTD, it is always going to be starting up with /ngfw and then var log messages. So we see the reloading snot complete, reloading snot and reload complete. And if you notice, the process ID is exactly the same as what it was before prior to the snot reload. However, in case of snot restart, here we see one set of we see again 7 different process IDs. And here these are the messages that we see for snot reload in the var log messages. And if you now notice the PIDs associated with snot, they are completely different as what they were before. So at least up to 6.2 version, there were quite a few, there are 25 different combinations of configuration changes that would have triggered a snot restart during deployment. So basically these different configuration changes will always have a condition wherein your snot restarts, which would in turn cause a traffic interruption on the firewall. So starting from 6.2.1, we have reduced them down to roughly around 20. And wherein if you are making changes to those specific configurations, like for example your VDB or SRU updates, we will trigger a snot restart. And some other changes would involve adding an SSL policy or so these sort of changes will still trigger a snot restart. But at this stage, if you're just making a normal policy deployment without any without using any major LSAN functionalities, we definitely do not we just do a snot reload over a snot restart. And one thing to make note of here is, again, using pre-filter policy for fast path. In this condition, it is generally recommended because of the restart. We can see conditions wherein the traffic is going to be interrupted, because of which is why we generally suggest, if in case that if you are having high critical traffic or wherein the traffic should not be interrupted because of snot restart, it is generally recommended that we set the action, we configure a pre-filter policy and set it to fast path, so that traffic is only processed by the ASA and it is never sent to snot. And in these conditions, because the traffic is only processed by ASA, during policy deployments, we will not be seeing an outages for that traffic at all. And in 6.2 onwards, for inline sets, which is supported on FTD, we can still permit the traffic through during snot restart, and this is only in case if you're using inline sets. Your normal interface mode that you have, that is either if you're configuring it in routed or transparent mode, in those conditions we will continue to see a traffic drop. But in case of inline sets configuration, you can actually, if you do have an option that stating if in case the snot goes down, we continue to forward the traffic through without dropping it. So as I mentioned, in routed or switcher interfaces, traffic continues to get dropped. So some of the best practices that we are suggesting from ACL accessless ACP processing is, again, one more point here is use pre-filter for fast path rules for big fat flows. So basically we have a limitation if there is high amount of data traffic passing through the firewall, wherein you are having one single flow and there is large amount of data passing through it. It is always best to, and if it's a trusted traffic, it is always best to fast path the traffic and not send the traffic to snot, because in these conditions it can lead to an instance wherein because it is one giant flow, we basically will always have the traffic to one snot instance, and that can lead to conditions wherein if there is any other traffic which is passing through, and if that traffic gets hashed again to that same snot instance, it can lead to conditions wherein other traffic, whichever gets hashed to that specific snot instance, will be experiencing some sort of delays or latency for the traffic. Hence, if there is any big fat flows or any specific flows in the network wherein we are seeing huge amount of data traffic pass through, it is always recommended that we do a fast path on the traffic instead of actually sending the traffic over to snot. And the next suggestion is more specific rules have to be placed at the top of the access control policy. So it's basically indicating that as long as you're trusting the traffic or if you're blocking the traffic, go ahead and place them as initial rules. If you are performing any sort of inspection on the traffic, like for example, be it IPS or file policy or QoS, these all have to come at the bottom of the list, because the way the snot engine evaluates these rules, we basically do a top-down approach. So if in case you have any rules at the top of the list wherein you're performing file policy and IPS, but then you have the next rule after that, which is what is permitting the traffic, we will still be performing the file policy and the IPS check on that specific rule, and only then will the next rule be evaluated. So that can cause a bit of a latency in that sort of a traffic flow. So it is always so you need to always ensure that more specific rules, be it if you know that the traffic has to be blocked, go ahead and block it, make it as rule number 1. If you know that the traffic has to be permitted through and if it has to be trusted without any inspections, place that higher up the order. But if it involves something like malware file analysis or IPS, place it at the bottom of the list. That way we evaluate rules in a better way and the snot should not be too much overloaded with that. And one more thing is, rule expansion from Lena side, we would be basically expanding the rules, while in snot, we basically would be having the same number of rules. We would not be expanding it too much from the snot side. So we are moving into the packet flow from snot side in a bit more detail here. So the first, mentioning DAC earlier as well. So DAC basically stands for Data Acquisition Library. So this is basically acting as an interface between the ASA and snot. Now what happens in DAC is we basically will be communicating something like this. So the DAC will be communicating with the data path processes, and then through a separate channel called Packet Data Transport System called as a PDTS. So what basically happens here in packet processing is first the packet comes in and we basically place the packet in something called as a DMA shared memory, and once the data path starts looking into this data path processes from the ASA side. So we start processing the packet here. So this is up till UNAT, pre-filter, L3, L4, ACL. So this is what data path process takes care of. So we start processing the packet here, and depending on the L4 action that you have, if the action is set to, if in case your pre-filter action is set to fast path, we would not be placing this here. If the action is set to analyze, if your action is set to analyze here and L3, L4, ACL is set to allow or trust, we then we add a pointer on the PDTS TX ring indicating this packet's location. If it is fast path, we do not do this. If the traffic is fast path over pre-filter, we will not be performing step number 3 here. After this, from the snot side, snot would also have multiple instances running. The snot will basically be querying the PDTS TX rings, and it would be checking as to what memory or the pointer locations, and based on which the snot will pick up this pointer location from the PDTS TX ring, and once it gets that pointer location, it will then access this specific packet from the DMA memory, And once that happens, it then goes through its snort processing, and once it is completed, it will then place that back into the PDTS RX ring, and it will basically be specifying the verdict. Here it is not actually specifying the packet, it is more like it will just specify the verdict of that specific packet as to whether it has to be permitted or if it has to be allowed or if it has to be blocked. And then the data path will specifically look into the PDTS RX ring, and then depending on the checking the verdict, it will then process the traffic and then send it out through the external interface. This is what basically DAC does here. So these are some snort statistics that we have. You can basically be verifying this from the Lena side itself. So you can do a show snort statistics. So the pass packets is wherein whenever the snort send a verdict of pass, these are the counters that we see. Block packets is verdict block was sent. Injected packets are conditions wherein we are sending a reset back to the client. So whenever you are setting an action with, say, something like block with reset, or if any of the preprocessors are triggering a condition when the packet is incorrect, at that stage the reset is always sent by snort. So whenever snort sends a reset packet back to the client, we basically see injected packets in these conditions. So that is what injected packet stands for. And the start of flow events and end of flow events is a condition wherein if you have fast path enabled on the pre-filter policy. So given the case that we are not actually sending the traffic over to snort for when the action is set to fast path, we still have to log that connection event on the FMC. So in order for that connection event to actually be logged on the FMC, we basically send information back to snort indicating that this connection was created and we have basically created a fast path for this specific traffic, based on which, although snort doesn't actually see the traffic, it will then log this event in the FMC indicating that that specific traffic went through the fast path over the normal traffic processing via snort. And end of flow is basically, start of flow is basically connection creation of those, and end of flow events is basically when that connection gets toned down, we indicate snort telling that the connection is down. And the packets bypass, snort down and snort busy, this is for inline sets only. We would not be seeing this in routed or transparent mode firewalls. So because this is what we indicated earlier, so this is supported only on inline sets. So it indicates how many packets are permitted through when snort was busy and when snort was down. So these two counters are only applicable in case of inline sets. Now, in addition to performing all these actions, the DAC then sends the traffic over to the preprocessors or the packet decoder. So here is what we basically do at this stage is we basically start segmenting the specific packet. So we start stripping away the IP layer information, the TCP layer information, and the data application layer information, and we start performing, the preprocessors start performing their functions on them to verify as to whether the packet is correct, the legitimacy of the packet, and the TCP checks are performed at this stage, and the application identification is taken care at this stage as well. And here is wherein we, and in case of TCP stream processor, we basically associated with stream 5, and the signature ID for that is GID 129. So under IPS rules, if you just filter for rule 129, we would basically see the entire TCP state checks which is being performed by the preprocessors which are being performed on the TCP preprocessors that are being performed on the TCP checks that is being performed on these packets. And in case if there is any preprocessor drops that happens, you would basically see it in the capture trace of the firewall again. As you can see here, it shows up as an IPS event, and it specifies which group ID or the preprocessor dropped it, and in that specific group ID which signature dropped it. So you can basically check if you are doing a capture with trace on the firewall, you would see the specific event showing up in the capture trace. And as I had mentioned earlier, there is also a condition wherein we can modify the packet. So if you are checking this option here, we are basically removing the data on send. So if in case the data packet, if in case you are receiving a send packet which contains data, so we go ahead and remove the data from it. So when that happens in Snot, when Snot sends a verdict back, you would actually see a verdict of replace, and then along with that we actually send a pass. So this is when we actually see a verdict of replace. Whenever the preprocessors make any changes to the packet, wherein we only make a small change in the packet, but then the packet size continues to remain the same. When that sort of normalization happens, we send a verdict of replace along, and we continue to forward the traffic out. So then we move on to security intelligence. So once the ELF decoding is completed, we then do the SI on IP level first. So this is an early detection drop. So because given that we are getting this as an updated Talos feed on the FMC, and then that gets updated over to the FTD. So depending on these feeds, it is the earliest check that can be done. So we go ahead and drop the traffic almost immediately, just purely based on IP level. And we do not perform any other checks at this stage. So this is probably the fastest drop that is being performed. And we perform another SI DNS URL check after SSL decryption, because if in case it is encrypted traffic, so as the DNS or URL, especially in case of HTTPS traffic, we will not be, without SSL decryption, we will not be able to identify the URL which needs to be blocked, even if it is a malicious URL. So in order to identify that URL or the application itself, the SSL decryption has to happen first, because of which is we do the second section of DNS and URL blacklist on security intelligence of DNS and URL after SSL decryption. And in case of FTD, we basically, again, I'm specifying here only for FTD platforms. So in case of URL, we will be storing the location under ngfw var sf si URL download. And in case of DNS, it is going to be SI DNS download. And in case of IPREP, it is going to be IP, it is going to be IP reputation download. So in case of normal FirePOWER appliances, we will not be seeing the ngfw. It is just going to be straightforward /var sf si URL download, and similarly the others. And this is how the file would look like depending upon what your security intelligence configuration is. So we would, under this, here I've given an example of IP reputation. So the grep BLF actually stands for blacklisted IP addresses. So if you basically open up under this specific location under IP reputation download, you would have this specific file .blf, which is basically the blacklisted IPs. If you view this file, you would actually see the Cisco intelligence feed, and in this case I'm just specifying the category of bots in my security intelligence configuration, and it gives you the IP address list as to what all are going to be blocked via SI. You would see something similar for DNS as well as URL under DNS and under URL download as well. And packets which are getting dropped by SI security intelligence under ASA engine capture trace, we would be capturing it under ASA engine as well under capture trace, and we would be seeing it under the FMC connection events as well. And under reputation, you can actually clearly see here it shows up as blacklisted and it is getting dropped. And here it tells you the reason as well. It is being blocked by SI/reputation. So under capture trace, we generally see why that traffic is actually getting blocked, and that is almost pretty easy to figure this out. Moving on to SSL decryption, FTD basically supports two types of SSL decryption on the firewall. One is called as decrypt known key, and one is called as decrypt resign. When it comes to decrypt no key, it is basically a condition wherein you are owning the HTTPS server which is probably you're owning the HTTPS server, and this is something in your environment wherein you're providing access to it from the external world. And we basically copy that HTTPS server, that server's certificate and private key on the FTD, and then use that for decrypting the traffic specifically only for that specific server alone. We do not perform, so we perform the decryption on the FTD and then send the traffic over to, we re-encrypt the traffic again and then send the traffic over to the server. And when the traffic is sent back, we perform decryption using the key again and then re-encrypt it back and then send it back to the client. So that is how it basically works in case of decrypt no key. In case of decrypt resign, we basically do something like a man in the middle. So it is more of a complete TCP proxy that we do in this case. So the entire client hello, server hello is all completely proxied by the FTD appliance, by the FTD. So whatever client hello the FTD actually receives from the client, it will be proxied by it, and then the FTD would be sending a totally different client hello to the end destination. And similarly, we would have something like an SSL handshake happening from the client to the FTD first, and as well as from the FTD to the server. So it is a complete TCP proxy which happens in case of decrypt resign. And we also support client hello modification. So this is enabled by default, as I mentioned earlier. So whatever client hello that we receive, that is not going to be the same client hello which exits out of the FTD. So it would be sending its own client hello outside. And the main thing to note here is in case of performing SSL decryption, because currently we do not support hardware acceleration on this, there is going to be a significant performance degradation here, and that is, we have seen up to 80% performance degradation. So that is a bit of a drawback in this feature, especially if in case you are doing SSL decryption. The L7 ACL policy we've already looked up earlier. That is basically your NGFW rules that we are checking. And we basically perform the NGFW rule evaluation, and then after that we then move on to QoS classification. So QoS rate limiting, we started on the FTD from 6.1. We still do not support traffic shaping and policing on the firewall. So what happens in QoS is the classification is actually done by the SNOT engine, but it doesn't really rate limit the traffic on the SNOT itself. The rate limiting is actually happening on the Lena side. So that is why you actually see the classification happens here while the enforcement happens at the ASA engine. And then we now move on to file policy or AMP. File policy provides a few different functionalities here. So we can use it to detect files that is coming in that are passing through the network, or we can block files, we can do a malware cloud lookup or block malware. Detect files and block files, it should be, you don't really require any license for this. It should be able to detect files and block files without having an AMP license for your system. But in case if you're doing malware cloud lookup and block malware, you would need to have an AMP license on the platform, else you would not be able to do that. So we basically, in case of detecting files, we only check the first 1460 bytes of the packet and then determine what type of file it is, and then we make a log of that specific event indicating that this is the file that is passed through. And in case of block files also, it is the same condition. We only investigate the first 1460 bytes, based on which we determine what the file type is. And if that specific file type is set to block, we would go ahead and block it. And in case of malware cloud lookup, we would be calculating a SHA value for that specific file, and we would be sending that SHA value to the cloud for analysis. And depending on the cloud's disposition on that specific file, on whether it is a malware or not, it would be either permitting the traffic, it would allow that file to pass through, or it will go ahead and drop it. Along with this, even it can perform local analysis as well. And in case of local analysis, it can do an addition. We have a few other options which we will be discussing later. And Then in case of block malware, yeah, again, this is if in case we basically we perform a local, this is more of performing a local analysis on the file, and if it is able to determine, if it is locally able to determine that the file is malicious or if it is a malware, it goes ahead and drops it. Additionally, in case of block malware, we have a few other options which I would be discussing in the next slide. So this is a condition wherein whenever we perform a cloud lookup, in case if we are not sure what type of file it is, so once the file passes through the network, we basically store the file. We not exactly store the file as such. We do a cloud lookup for that specific file, and in case if the cloud disposition comes back as clean, we save that specific hash value in the cache for up to 4 hours. This is because in case if because this is a trusted file, and if we assume that that file is already if that file passes through the network again, instead of performing a cloud lookup again, we need not perform that cloud lookup again, because of which it starts working correctly. We need not do a cloud lookup again. But in case of malware, in case of the file is considered as malware by the cloud disposition, so we basically store that hash value in the cache for only an hour. The reason why we do that is because there have been conditions wherein initially the cloud lookup can dispose the file as a malware, but after later analysis it would probably be considered as a non-malware file, because of which in case if the cloud disposition returns the file type as malware, so we generally do not cache it for more than an hour, because if in case the cloud disposition changes, it doesn't get updated that immediately, because of which it runs into a problem. And in the next disposition is unknown. Disposition unknown basically indicates that even the cloud lookup has not, the cloud lookup also didn't come up with any result as such. It has not been able to determine whether the file is clean or if it is a malware. And under this condition also, we only save it in the cache for about an hour. And in case of custom detection and unavailable basically is a condition wherein we could not perform a cloud lookup, and we do not save any of those in cache for any point in time. So these were the actions that was discussed earlier, that I mentioned earlier. In case of block malware, we do have a few options here. We can selectively choose all of them, or you can choose only specific actions under these criteria. Now, in case of block malware, the additional action that you can perform on this is, one is perform a Sparrow analysis for exe traffic. So it will be basically performing an analysis on the file, and it would be submitting the signature to the AMP cloud. And in case of dynamic analysis, it is going to be directly sending the file over to the AMP cloud for analysis. And in case of capacity handling, what it basically does is the FMC will store that file which is needed for dynamic analysis. This is until the cloud comes up with a disposition. Once the cloud comes up with a disposition, it is going to go ahead and delete the file. But yeah, until the cloud comes up with a disposition, it is going to be storing it as in the capacity handling if that is enabled. And local malware analysis basically indicates that if it examines a file and if it contains malware, it goes ahead and directly creates a report of the file indicating why it was considered as a malware. And then the recommended action is reset. So basically we do not permit the traffic to pass through, and we go ahead and straight away block that connection and prevent the file transfer from happening. So we discussed earlier on the number of packets or some advanced options which is related to file policy. So you would basically be finding this under your ACP rules under advanced tab. So as I had mentioned earlier, the settings that we discussed earlier, that is we are determining the file type just based on the initial 1460 bytes. That is all, those all settings you would find it under the advanced settings of the access control policy under file and malware settings. So the first section, as you can see, limit the number of bytes inspected when doing type detection. So here is wherein you specify the 1460 value, wherein by default we only look at the first 1460 bytes, and then based on that we determine what type of file it is, and we either permit the traffic through or block the traffic. That is in case if it is not a malware, or if you do not have configured any deny rules for any specific file types to be blocked. And the next one is how long it needs to wait for the cloud lookup. If in case it doesn't wait, it will basically permit the traffic through. And by default, for any malware types, what we do is we only calculate a short value for only up to, if the file size is up to 10 MB. In case if the file size is more than 10 MB, we do not calculate the SHA value for it. And the next one is what type of files are being, what is the minimum file size that we can store when we have set the action to store the files locally. In this case, what you are specifying is if the file size is smaller than 6 KB, we will not be capturing that file, or we will not be storing that in a local database. And the other option is what is the maximum file that we can store. We cannot go beyond 1 MB, so we only store up to a file of 1 MB locally on the FMC's database. So the minimum file size, the next one is the minimum file size that can be sent to the dynamic analysis, or this is basically to the cloud how much data that we can send. So the minimum file size is 0, so we can actually, so this is basically the minimum value and this is the maximum value that of the file size that can be sent to the cloud for performing dynamic analysis. Next, we are moving on to a feature called as flow offload. So this functionality is a bit different from the flow offload that we discussed earlier in case of when the traffic is only being evaluated up to layer 7 snot rule and then being offloaded to DAC. This feature is specifically only supported on 9300 and 4100 platforms, and this is considering a case wherein your pre-filter rule has a fast path configured for the traffic, wherein the entire traffic is only processed by Lena and not by the ACE engine and not by the snot engine. So during these conditions, based on the 9300 and the 4100 security module architecture, we can offload the flow to something called as a cruise adapter, which would take care of processing the traffic completely, and that way you would actually be getting higher performance in the traffic, and we would not be seeing too much, and the amount of latency that we see for this when the flow is offloaded is going to be extremely less whenever the flow is offloaded. So this is supported, again, as I mentioned earlier, supported only on 9300 and 4100, and this is starting from 6.1. And this feature, if in case you are running any version of code beyond 6.1, gets enabled by default. So there is the flow offload functionality is enabled by default. So there is no need to explicitly enable the functionality. All you need to do is have a configured pre-filter rule, and the action has to be set to fast path. So as long as that is done, the flow will be offloaded, and wherein the traffic will then be completely processed by cruise and not by the FTD anymore. So why flow offload? As I mentioned earlier, in case of data center FTD deployments, wherein if you are having huge amount of data being sent, so instead of we are performing an even better, instead of having an ACP rule set to trust, we are bypassing even the ASA side inspections as well with the flow offload functionality by setting the pre-filter action to trust to fast path, and at that stage even the ASA will no longer be, the ASA engine also will no longer be seeing the traffic, and the entire flow gets offloaded, and we see higher performance in these conditions. And again, as I mentioned, latency is also extremely reduced when the flow is offloaded. this is a basic architecture of how the flow offload looks like, of how the flow offload actually happens. So here we have the ingress, or basically you can actually consider this as the MIO complex, the MIO switch fabric complex that you have, and this is the entering of the security module. The traffic entering into the security module, we first hit something called as a cruise ASIC. Once the traffic enters cruise, we then send the traffic through to the LINA data or the ASA data plane. And from the ASA data plane, the general traffic processing looks something like this if I do not have a flow offload. So it will be ingress that coming in on cruise. It then traffic is then sent to LINA data plane. The traffic is then sent to SNOT. SNOT sends the traffic back to LINA, and LINA sends it back to cruise, and it goes out via the egress interface. This is how general flow processing happens. But once a flow is offloaded, what happens is we basically see the traffic ingressing on the cruise, and here itself the rewrite happens, and we directly send the traffic out via egress. So this path that we are seeing, that is from cruise over to LINA data plane SNOT, that doesn't happen anymore when the flow offload is happening. So this way, the entire FTD architecture or the FTD portion is completely bypassed for these flows. This is how a general TCP flow offload happens, and this is basically explaining at which stage is the flow offload happening from the 9300 or the 4100 perspective. So we have a few modules here. One is called as, the starting is called as RX classifier. So this classifier basically looks at control packets, and when we call control packets, in case of TCP, these are basically packets called, give me 1 minute. Okay, sorry about that. So let me restart on the flow offload here. So we have something called as the RX classifier initially. So in RX classifier, we basically start looking at control packets on, and when we call control packets, in case of TCP, those are going to be SYN packets, and FIN packets is what we consider as control packets. And then we have, and whenever you receive any packet which contains a SYN or a FIN, we will be forwarding that traffic directly to the LINA data path, and we will not be doing any of these lookups. So then we have the flow table. So what LINA does is, once the flow is offloaded, we basically create a flow table within cruise, so indicating at which stage, indicating that the flow needs to be offloaded. So that is where the flow offload happens. And this is the this is where cruise offload DP is wherein we perform the L3, L2 rewrite that needs to happen in the packet. So at this stage is wherein the rewrite happens. And then we have the flow offload manager. This is basically acting as an API for offloading the flow from LINA over to cruise. And LINA is this here is wherein our FTD engine starts, and here is our LINA data path, and then we have the SNOT. So it initially starts off something like this, wherein we first receive a SYN packet. As I mentioned, it first is the RX classifier, and because this is a control packet, being that this is a SYN, we directly send the packet over to LINA, and LINA will perform the ACP rule checks, and it will try to determine if the action is set to fast path. If the action is set to fast path, it will just send a notification to SNOT. It will send a flow create event to SNOT, and this is when the connection is logged on the FMC, indicating that this connection is now created as fast path. And once this is done, LINA will then send the packet back out through its and it will leave out via the egress interface. Now the server replies back with a SYNAC, And again, since this is a SYN packet, again, because it is control, we send the traffic directly to Lena. And yeah, now Lena again sends the packet back, sends this packet back to the client, sends the SYN ACK back to the client, because a connection already exists. Because we have a SYN, for the SYN we have already created a 30-second connection. And at this stage, the client sends it back, sends an ACK back. At this stage, given that this is just an ACK, it is no longer containing any SYN. So now this RX classifier we hit, and then whenever the RX classifier is hit, we then always forward the traffic to this flow table, wherein it will basically check if a flow exists or not. So given that this is an ACK packet, RX classifier gets hit, and then we perform a flow table lookup. However, at this stage, because the flow hasn't offloaded yet, we send the traffic over to Lena once again, because there is no flow available in the flow table. We then we send the traffic over to Lena. Now, given that the three-way handshake is completed at least from one direction, so from client side, the forward flow is complete. So we basically, while sending the packet back through, we intimate the flow offload, the offload manager to offload the flow, and then also, and the flow offload manager will add a flow entry to the flow table. And now the server responds back with a push or a data packet. And again, given that this is not a SYN packet, the RX classifier is hit, and we check the flow table. Now, in case of flow table, keep in mind this has to have both the forward flow as well as the return flow. So this is not the same terminology or of what we call as a connection on Lena. So this forward flow meaning client to server, and the reverse flow meaning server to client. So again, because the flow offload doesn't have any data for the server to client flow, we again send the traffic back to the ASA data path processing. And at this stage, given that this is an existing connection, now Lena ASA sends the packet back through the exit interface, and at that stage it will intimate the offload manager to offload the reverse flow now, and the offload manager will add a flow table entry for the reverse flow at this stage. And along with that, during this process, at least up to packet number 4, the flow offload doesn't happen, and only after packet number 4 is when the offload happens in case of TCP traffic. And from here on, the crews will already get the rewrite rules. So here is wherein we perform the layer 2 MAC address rewrite, wherein, because that this is considering that this is routed mode traffic, so the initial ingress traffic, and when it egresses out, the destination MAC changes. So those sort of rewrites is performed. Those rewrite rules are programmed into crews here, for the forward flow as well as for the reverse flow. So now we start seeing conditions wherein for this push data, when the ACK comes back in, it hits the RX classifier hits the flow table finds the flow, because of which it then sends the traffic to crews. Crews performs the MAC rewrites, and then directly sends the packet back and from here on, we no longer send the traffic to the Lena data path. And similarly, when the reverse packet comes back in from the server side, it again hits the classifier, it hits the flow table, it hits the cruise offload, rewrite happens, and then sends the packet back. So the main thing to note here is, whenever you are performing a flow offload, because of this functionality, wherein the traffic is never sent to Lena data path, if you are performing any capture for this specific traffic, you would only see like 4 packets initially. After that, because the entire flow is offloaded, you would not see this packet even getting captured on the FTD captures. So this is something that is very important, and from a troubleshooting perspective as well, because yeah, it would basically indicate that we are not really seeing any traffic on the Lena on the FTD side, but then yeah, the actual traffic will be offloaded and it will definitely be working. So this is something that we need to be keeping mind of. And now when it comes to flow termination, again, we first receive a fin packet, and again, given that this is again a control packet, given that it is a fin, the RX classifier will basically send the traffic directly to Lena. And as soon as I receive the fin packet here, we remove the forward flow. This is considering a case wherein I'm receiving the fin from the client. So that is why I'm removing the forward flow entry. So we intimate the offload manager API, and then the offload manager API removes the rewrite rules and as well as removes the flow entry from the flow table, and then sends the packet out. And when the server responds back with a FINAC, the same thing happens. Given that this packet contains a fin, we perform the RX classifier directly sends the traffic to Lena or ASA data path, and then ASA data path, when it sends a packet out, intimates the offload manager to remove the reverse flow and the MAC rewrites for that, and then the packet is sent out. Now when the server responds back with the ACK for the final fin from the client, it hits the RX classifier, and because this is not containing SYN or fin, we then perform a flow table lookup, and then when the flow table lookup basically will not have any entry, because of which, because of the previous condition wherein it removed the flow entry, it then forwards the traffic over to Lena data path, which intimates now that the connection is closed. And when this connection gets closed, we create an event, we send an event to Snort indicating that the flow is closed, and this event is then generated on the FMC and that is when we see on the FMC connection events that the flow has been terminated. You would see a similar sort of a flow offload happening for UDP traffic as well, although I do not have a slide for that. But in case of UDP traffic, we do not really have any control based traffic. So it is definitely going to be something as receiving this ACK packet here. So the first packet comes in, the RX classifier receives the packet, it will do a flow lookup, it doesn't find the flow, sends the traffic to Lena, and then Lena adds the flow offload entries. And similarly, when we receive the reverse flow for that, it comes back to the RX classifier, it doesn't find the reverse flow, and then it performs, and then it sends to Lena adds the flow offload entry. So in UDP traffic, you would basically see only something like this ACK, push data, ACK packets that you're seeing in case of TCP. So we do not really have any control packets in case of UDP. And the way the connection gets toned down is purely based on timeout. So as soon as the connection gets timed out on Lena, we basically intimate the offload manager API to tear down the flow entries from cruise as well as the flow table, and that is when the entries are removed from these entries. So this is how a general flow offload configuration looks like. This is nothing special in this. So I'm just creating a fast path rule. So you need to have a pre-filter rule wherein the action has to be fast path. Only then will the flow be offloaded. So this is how the configuration looks like. So from the FMC perspective. So moving on. And if you're verifying it from the CLI, if you do a show run access list, so you can see this was already covered earlier. So this is the pre-filter policy. And we basically create an advanced trust rule for that specific source to the specific destination. These are a few other commands that you can use for flow offload verification. So if you do some commands are as below. So one is show flow offload info. You can see something called as the current running state and the user configured state. So in case of FTDs, you would generally see this both as enabled and enabled. You would never see a condition where an user configured is enabled while current running state is disabled. We do have this functionality for ASA platforms running on these 9300 platforms. So in case of ASA platforms, the flow offload has to be configured manually. So, but that is not the case in case of FTD and that is the reason why you would never see this sort of a condition wherein the user is enabled while current running state is disabled. Even if you do see that sort of a state, all you need to do is just reboot the FTD application, and as soon as it is rebooted and when it comes back up, it would indicate that the current running state is also enabled, And if in case it is disabled, you generally do get a warning indicating that you need to reboot the appliance. The next command is the show flow offload info detail. So this is basically giving you the same information in a bit more detail. So it tells you what cores are allocated from the app instance perspective, from the app instance or from the FTD instance. And it also indicates how much traffic has, what the number of bytes for the traffic counter is. And for offloaded flows, we have introduced a new flag for these connections. So if you perform a show con and if you check the offloaded flow connections, you would basically see something called as an -o, which indicates that the flow is completely offloaded. So this indicates that the bytes counter is mainly incremented based on the data that it receives from crews. So that offload manager API that we have in place basically will be communicating with crews to retrieve the bytes information as to how much bytes has been transferred, based on which we basically see the bytes information in the showcon output as well. And in order to actually identify in a bit more detail on what all flows are offloaded, you can actually do a show specifically to identify only which flows got offloaded. You can do a show flow offload flow, and that gives you the specific details of which flow got offloaded and nothing else. And if you perform if you have a detail output on this, you would also see the MAC entries rewrite which happens or which gets programmed from the crew's perspective. And we can use that for verification as to whether the MAC entry to which the destination MAC, whether the correct destination MAC has been rewritten or not. That's the end of my session for now. My colleague will be taking over from a performance perspective and some best practices. But from the session so far, do you guys have any questions? Okay, I'll probably hand over this, continue the session over to my colleague Sunil. He would be taking care of the remainder of the session, which is basically something to do with FTD optimization and some performance improvements that has been made with regard to the FTD and what can be done for performance issues in case of FTD or FirePOWER.
Rahul, do you want me to pass the ball to Sunil? Yeah, yes, no.
Hello everyone. My name is Sunil. I'm working with FirePOWER TAC since last 3.5 years, working on Snort and supporting the customer on SourceFire and the FirePOWER products. So today in my session, the most of performance optimization will be on the Snort side, which means the application layer deep packet inspection, where how we can figure it out what are the performance bottlenecks and how we can optimize those parameters. Okay, let's start. So slides will be covering the what are the factors for the performance bottleneck, performance tuning, and some of the best practices. So the first parameter is the intelligence application bypass. This feature has been introduced since 6.0 version, and what basically it does, so when the traffic comes to the detection engine, the snort, and we usually see the high CPU on the detection engine, and we need to figure it out what kind of flow and what kind of traffic, how much rate of the traffic which is causing the bottleneck on the detection engine. So one way is that we can do, we enable certain configuration, enable certain debugs, and then figure it out what is how we can and by that way we can figure out the flow which can be trusted or bypassed from which flow is creating the problem into the detection engine. The other way is the intelligent application bypass. This is the feature is being introduced in 6.0, which takes the performance data on a regular interval and match as per our configuration. So let's assume that CPU of 80% in my network is something wrong with the network. So we can define the threshold of CPU of 80%, and the system keep monitoring the data, the CPU, and try to match what is being configured. And if the threshold matches, it will create a dynamic rule to bypass those traffic from the snort detection. So it will send the instruction to the Lina saying that do not send such type of traffic because it is creating a bottleneck or a performance impact on the system, on the detection engine. So the purpose is to offload the traffic in case of the performance issues. So to trigger the condition of intelligent application bypass, the detection, the snort should be under the performance issues, and there could be flow. Suppose let's assume that I have set, if there is a performance impact, I know which application in my network is running, and I want to allow those applications to bypass in case of the performance issues. So let's say that there's an attack and there's another traffic is also going through the network. Let's assume a backup. So backup is taking, let's assume that 50% performance. An attack happens. Because of that, performance has reached to the 80%, 90%. So system, what we can do in the system, if the performance reaches to 80%, just offload the application, the backup application, so that right resources is given to the attack traffic. So there are certain performance criteria on which we can define the threshold and the time frame where system will collect the statistics and try to compare those statistics with this performance matrix defined by us. So one of is the performance processor load, drop packets, packet latency, and the flow rate. In terms of the flow matrix, amount, byte count, packet count, velocity of flow in bytes per second, duration of flow in seconds. Let me show the next slide. Okay. So this intelligent application bypass setting is part of the access control policy in the advanced section. And if you look into the advanced and in the bottom, intelligence application bypass settings. So these are the parameters for the intelligent application bypass settings. There are three states. One is off, on, and test. Off, which means is disabled. On when we configure it, when we configure the intelligent application bypass, if threshold matches, then offload the traffic. And the test, the third state is test, which basically means that it will keep monitoring the sessions and will generate a connection event saying that this traffic can be offloaded because this threshold is matching. So the test is just to test the configuration and to figure it out in the network which flow can be bypassed. Performance sample interval is the time frame which we need to define about the collecting the data within a certain time interval. In application filter, we can define a trusted application. Let's say that in case of performance issue, trust these kind of application which can be defined in this option. The next is application including unidentified application. Suppose I don't know which application it is, so we can configure this option to allow all the traffic of that kind where the performance it is going on. To configure the application, to trigger the condition, there are two parameters. One is based on the performance threshold. The second is the flow threshold. In the performance threshold, we can define based on the percentage of packet drops, CPU utilization, amount of latency being introduced by the detection engine into the packet, flow rate, how much flow are coming to the detection engine per second. And same way, we can do the we can configure the condition based on the flow as well, byte per flow, which means that let's assume that a user is trying to download a 10 gig of file from a server, and that 10 gig of file is creating a high CPU, a performance impact on the detection engine. We can define a value over here saying that if there is a flow which contains 1 gig or more data, then offload that traffic. Same way, we can define the flow packets per flow, number of packets into a flow. If that number reaches, just offload the connection. Duration of flow, let's say that a connection is up for 1 hour, then we can trigger the condition. If the connection is more than an hour, just offload the traffic. And the flow velocity, kilobytes per second, which means that if the rate of the traffic in terms of kilobytes is that number, if 10 MB per second, if that volume of traffic is coming into a single flow, then offload the traffic. So there's a multiple conditions. So what we usually do to make a better performance on the system, we can enable those parameters in the test environment. We can identify which parameters are including which parameters can include the performance threshold, performance impact in the network, and based on that we can optimize those parameters so that the detection engine gets the right resource and perform the right inspection on the traffic. Okay, so next feature is the automatic application bypass, which usually tests the latency into the traffic. So let's assume that there's a traffic coming to the Snort engine, and that traffic is taking a longer time, more than expected. Let's assume that certain traffic, so when the traffic comes to detection engine, it reassembles the packet and then try to match the rule. If by any reason the detection engine has received few packets and is waiting for the another few packets, and let's take that this is a one session. If there's 1,000 of sessions of like that, there's a probability that such type of session can increase the memory in the detection engine, and such type of traffic can because all the resources is being used for such type of traffic, there's no more resources for the new connection. So what the automatic application bypass does, it determines those type of traffic and restart itself so that it can get the resources again. And when it restarts, it generates a core file. That core file will be used to determine what kind of traffic it is, which is causing a performance impact on the detection engine. So once the customer has to share the core file with the TAC, and we can let you know this traffic has a bad behavior, and that's something we need to look on that traffic. So this parameter can be configured into the device management, and we can edit the device. And in the device tab over here at the bottom in the advanced section, we can configure the automatic application bypass, and we can define the time frame in the milliseconds where when the time frame defines how much time the detection engine will hold such type of session before it restarts. So when application bypass triggers, it gives an alert into the var log messages file saying that the AAB has been kicked in and there is a detection engine has been restarted, and a core file is generated, and the core file will be available into the ngfw var common directory. So it will say that the snort and the PID of the snort engine on which this ABB has been triggered. So that way we can avoid the unwanted traffic which can create problem into the detection engine. We can determine those type of sessions and can do the right things about those sessions, and because the system restart again, it can start the detection, the inspection again. So it will not go into a stuck state. Rule profiling. So rule profiling is usually being done when there is a high CPU because of the configuration. So the IPS has suppose n number of rules. Let's assume the 9,000 of rules, and there is a component into a rule or in the detection engine which is creating the problem, and because of that there is a high CPU into the detection engine. So let's assume that there is no high bandwidth even though there is a high CPU. Traffic rate is very slow, but still there is a high CPU on the detection engine. So first thing we can check in terms of traffic rates, and if there's no issue in terms of bandwidth on the rate of the traffic, then we usually look into the rule profiling. So rule profiling gives us the more granular data about which component into the detection engine, into the snort, can cause a high CPU. So the CPU cycles are given to the snort engine. So if a component into the snort is using a more CPU cycles rather than other, but that component not supposed to take that much of the CPU cycle. So in that situation, we can determine which component is being has a wrong configuration or issue. So we can optimize on that basis. So to enable the rule profiling, so there's a command system support run rule profiling, and 15. 15 is the time frame for how long you want to enable this rule profiling. So once you enable the rule profiling, the system detection engine will restart and will log more granular data into the hard drive about the component and the number of CPU cycles being used. After the 15 minutes, the detection engine will restart again, and whatever the configuration was earlier, it will be revert back. And a file will be created into the var common directory about those logs data. And this file, the customer has to share with the TAC to figure it out which component is causing the problem. So those statistics looks like the output given in the screenshot. It says that there is a preprocessor and the microseconds and the checks. So the node has a multiple component, and the CPU is divided, being used by those components. If the number of checks is high and the time is in microsecond is high, that means that that component is taking much more resources than other. So when we do the troubleshooting in this, we check the relatively outputs in a normal situation and in a situation where there is an issue, and when we compare it, we can check that this component doesn't look good, and troubleshooting is based on that component. So let's assume that detect here is about the detection engine, then MPS, rule evaluation, rule tree evaluation. So these are the component of the node. So once the system figured it out, there's a component which is taking high CPU, then the rule comes into the picture. So if there's a rule is being written wrongly, or it is not written in an optimized way, it can use a lot of CPU cycles. So in the SID column represents the SID of the node signature, and the checks represents the CPU cycle, and the microseconds represents the time frame being used by this SID. And average check and average check, how much time this rule has been trying to match, and how much time this rule has got triggered, average match, and average non-match, how much time this rule has not been triggered. So let's assume that there's a rule there's a rule into the system, and system is giving more resources. We can check the check column over here and the time frame. So it's taking more resources, but there is no match. Average no match is also high. So which means that there's a rule into the system is taking the resources, but none of the traffic is ever matched to that rule. So those type of rule can be disabled to optimize the configuration. So it depends rule to rule, which kind of rule, if it is SMTP, STTP, FTP, and if it is appropriate to disable, then yeah, by looking at this output, we suggest the customer to disable those rules and check the performance. Okay, so next feature is the flow IP profiling. So this is a part of intelligent application bypass. Intelligent bypass is an automated process. We just given the parameters, system keep monitoring those parameters and triggers an alert when the threshold match. In the same type of things we are doing in the flow IP profiling in a manual way. So the intelligent application bypass is not working properly and is not bypassing, offloading the traffic. In that situation, we can use this manual process to determine what kind of traffic. We can get the traffic statistics, such like the top talkers. If there is high CPU, how much bandwidth is being given to that detection engine. Because of that, there is a high CPU. It will give us more granular data in terms of IP, source port, destination port, so we can determine which traffic we can bypass from the detection engine. So we can make a trust rule or a pre-filter rule into the system, so that such traffic is being bypassed in a very initial stage. This manual process is also help us to determine the oversubscription in the detection engine. So this is just a procedure to enable the flow IP profiling into the system, and it just when you refer it into the system, you can go through this procedure and to enable the flow IP profiling. So this basically creates another file into the system, and we need to collect those files from the system. Once those statistics, those logs data being gathered, the customer can share those data with the TAC, and we'll let you know the which source and destination has more number of traffic in terms of flow, in terms of bandwidth, like that. So here is one of the screenshot of a traffic. So it says that so when we collect this data, we'll put this data into a script which give us a more appropriate output, which can be figure it out what kind of which can be used for gather the statistics related to traffic. So it says that there is a source and there is a destination, and that much of packet is being transferred. This is the bytes being transferred between these two IP addresses. So let's assume a scenario where a user is trying to download a 10 gig file, and at the same time we have enabled this data. So it will let us know that this is the source IP address and this is the destination IP address, where most of the traffic is being transmitted through the detection engine, and which is creating the problem into the detection engine. So we can have the data related to TCP, UDP, and based on the source and destination IP and the port number. So this output can help us to make the pre-filter rule and the trust rule for the traffic which doesn't require the inspection, such as a backup job between two servers, where there's a continuous flow of data every time. Those type of traffic does not require the inspection, and those kind of traffic can use a lot of CPU cycles in the detection engine. So we can use this method to determine those flows and can offload those flows and can give more resources to the detection engine for the other traffic. Okay, so next section is the latency-based performance setting. When we configured a NGFW firewall into the network, there's a probability that there is a high latency into the network, because a lot of components are involved, and there is each component is taking certain amount of time to inspect the traffic, and to avoid the latency into the traffic, there's two components in the detection engine. One is the packet latency threshold, and the second is the rule latency threshold. It is more likely an IPS inspection where customer has enabled more than 10,000 rules or even more than that. So system has to check all 10,000, 12,000 rules before it gets a verdict saying that if this traffic is malicious or not. So matching the 12,000 rules for a packet, for a certain traffic, it can take a lot of resources. If the traffic is abnormal or either detection engine is not working properly, then the impact will be on the traffic. There will be a latency into the traffic. So to avoid those latency, the detection engine has two type of threshold. One is the latency and other is the rule based. Okay. This component is being configured in the access control policy. When we added the access control policy in the advanced section, there is a parameter for this latency based performance setting. We'll look into the deep in the next slide. In terms of latency based performance setting, there are two timers. One is the elapsed time and one is the processing time. Elapsed time is 256 and the processing time is the time taken by the detection engine to inspect those packets. So let's assume that a packet comes to the detection engine, it performs the protocol based abnormality and then it try to match the 12,000 rules, and there's a elapsed timer, and as soon as we start processing the traffic, a processing timer is also start for that flow. If at a certain moment when the processing timer is taking more time rather than elapsed timer, so if it is processing the rules, let's assume that it matches the 8,000 rules and the processing timer is equal to the elapsed timer. That means that whatever the threshold we have given, it reached at the stage of 8,000 rules. At that moment, the detection engine will bypass that traffic from the detection engine, and the traffic will be given to the network again. So in this way, it usually helps the customer to stop the inspection of the packet when there is a lot of processing power being used by the detection engine. If there's a problem with the detection engine or either there's a slow traffic with, let's assume that the traffic, the system has to do the traffic packet reassembly. Suppose it gets 4 packet, is waiting for 1 more packet, but the timer expires. So at that situation, the system will offload the traffic so that the network traffic should not get the latency because of the firewall. So here's the time. So elapsed time is given as 256, and now when the packet comes to the detection in, the processing timer starts. It keeps moving from the packet decoding, then preprocessor protocol abnormality, and then it try to match the rules. So if let's assume that at the rule number 2 is like 9,000 rule, when at the rule number 9,000, the processing time is expired, it reaches to the elapsed time, then the packet will from the rule number 2 is come out from the detection engine, will be given to the network and will be sent to the end server or the client. These parameters we can change based on the network to network. For a slow network, this value should be higher. For a fast network, this value should be the smaller one. For the this latency based performance can also bypass an attack as well. So we need to consider that as well. So that's something we need to check based on the network, how much bandwidth it has and what kind of traffic it is, and based on that we can reconfigure it to get the best detection performance. Next is the rule latency threshold. what basically means that let's assume that there's 9,000 rules into the system, and there's a few rules which are written into a non-optimized way, and those rules and taking a lot of time in the processing. So there's a custom rule or a source fire rule which is wrongly written and is not optimized one. And let's assume that the packet starts here, comes to the detection engine. It tries to match the rule number 2, and when matching is when the packet payload is matching with the rule number 2, is taking a significant amount of time. If that significant amount is keep increasing, those type of traffic either be bypassed after a certain amount of time, and a lot of resources time is being used by that rule that's supposed not to be. That can also be that can also compromise the security, because that rule is creating a problem and the other rules are not matching because of that rule. So we need to figure it out, those rules that can be done by rule profiling, as we have discussed before. And because of this rule-based wrongly written rule, there shouldn't be any latency into the network. To avoid those type of latency because of a wrongly written rule, we can use rule latency threshold. So what it basically does, it starts a timer when the rule matching starts. If a packet matches a rules, and suppose such type of traffic, 5 packets are coming for matching that rule, and that rule is taking, every time it matches the rule, that rule, it takes, let's assume that 10 milliseconds. If that happens for n number of times, we can specify the time frame. If that packet, such type of traffic matching a rule, and that taking so much amount of time, and that happen n number of times, then disable that rule. So that disabling that rule, the other traffic will not be impacted because of that wrong rule. So we can define the threshold in that way. So is the rule handling threshold defined as, if a rule taking a 512 microseconds, and there are 3 packets, there are 3 consecutive packets which took the 512 millisecond or more than that, then disable that rule for another 10 seconds. So by doing that, we are dynamically disabling the rule so that the traffic latency will not increase. Benefit of rule-based latency threshold is we can avoid the excessive amount of processing time on a single rule, and in a period of the poor network performance, where the network performance is not good, the rule profiling helps to note that poor network performance can become more poor. We can avoid that situation from the rule-based latency threshold. Okay, thank you everyone. That's all from my side. Hey Rajesh.
So I believe most of the questions has been answered in Q&A panel. Prapaj, is there anything that you want Rahul or Sunil to address?
So that's it from the Parpan side. If anyone has any question, we can answer that.
Okay. Let's open the session for live Q&A. As usual, you can post your questions in the Q&A panel, or you can also use the raise hand option, and I can unmute you to speak out with your question.
There are no questions.
There has been questions on the recording and the deck. Yes, it will be shared to you via email in a few days. Yeah. CK, I just posted a link in the Q&A panel. You can also find the deck and the recording in that website of our previous webinars. CK, you're on. I just unmuted you.
Hello,
Rahul,
can you hear me
there?
now?
Yes, CK, please go ahead.
Yeah. Sorry. Yeah, I think the session was great. I just wanted to say thank you. Yeah, I was just after the recording. So, something wrong with my computer that I spoke and you guys couldn't hear me. So, yeah, did you say that you're going to have a link for us to access to the recording and slides?
Yeah, I posted a link in the Q&A panel. You can just follow that link and you will be landing in a library page where you can find all our previous webinars, recordings, and the presentations.
Okay, cool. Let me see. All right, that's it I have actually. Yeah.
Thank you.
I'll try to access the link. Thanks, guys. Yeah, great job.
So Rahul, do you have anything to add or we can wrap up the session?
Yeah, we are good from our side. Yeah, we can close it if there's no further question.
Great. Thank you, Rahul and team. And thanks again, everyone, for attending today's session. You will be presented with a code probably by next week. Once you clear it, you will get $100 Cisco rewards and a black belt support certification. As mentioned earlier, the recording will be shared to you via email within few days. Just a quick reminder, once you end the session, a short survey will automatically pop up on your screen. We appreciate if you could spare a minute and fill out the short survey to let us know of your experience. Thanks again and have a good day ahead. Bye, everyone.
Thank you.
Yeah, thank you.